See these bouncy balls here, guys? Well, they're actually top quality bouncy balls. Now, how do I know this? Well, it's because every time they hit the ground, they bounce back to 70% of their previous height, like so. Now, what we're going to do is we're actually going to have a look at a worked example of something just like this. So, let's check it out.
Alright, so it's time now to have a look at another application type question for exponential and logarithmic functions, but in this case, the equation of the function is not actually known. So let's go through and read it first of all, because that's our first step that we need to do, and that is a ball is dropped from a height of 5 meters and rebounds to 70% of its previous height with each bounce. Now for part A, we need to find a rule that describes the height of the ball with each bounce. For part B, we need to find the height of the ball after 4 bounces and then again after 6 bounces. And for part C, we need to sketch the graph of the height of the ball after n number of bounces. Now part 2 says go through and highlight the key information. So let's go through and do that. So the first thing is a ball is dropped from a height of 5 meters. So it's dropped from the height of 5 meters. That there is important because it's telling us our initial height. It then rebounds to 70% of its initial height. So 70% of its previous height with each bounce. And that's important too because it's telling us that every bounce it does this. Now what we need to do is go through and rewrite key information in dot points. Well, there's a few things going on here. We don't actually have an equation of the line, but we do have enough information to make one, as you'll see soon. So let's have a think about our initial height. Well, that there is equal to 5 meters. Now we also know that with every time that it bounces up to 70% of its previous height. So 70% of previous height with each bounce. Now in terms of our independent and our dependent variables, well, let's go through and identify those. So our independent variable, well, that's going to be the number of bounces. And our dependent variable, well, that's going to be the height, because the height will depend on how many bounces we've got. And of course, because we don't have an equation to represent this function, what we're going to need to use is the rule that you can see up in the top right hand corner of the screen. That is, y is equal to k times a to the power of x, where of course y is our dependent variable, k is our initial amount, a is the amount that the initial value is increasing or decreasing by, and x is the independent variable. So let's go through and answer the first question now, where it says find a rule that describes the height of the ball with each bounce. Well, let's go through and rewrite this information. So as we found before, our height will be our dependent variable, so our y is equal to our height, and what we'll actually call this is h. Now the next thing is we're looking for our k value. Well, our k value is our initial value, and our initial value is going to be 5 because that's how many meters high it starts off at. Now our a value, well, our a value is how much it's increasing or decreasing by each time. So with every bounce, it bounces to 70% of its previous height. So that means if I multiply the next number by 0.7 and then again by 0.7, it will get to 70% of its previous height. So therefore, our a value is equal to 0.7. And now our x value, well, that's going to be the independent variable, so therefore that's going to be the number of bounces. So that's number of bounces, and we'll call this n. So let's go through and rewrite out our equation. That is, a y is equal to k times a to the power of x. So we have y is equal to k times a to the power of x. But let's go through and substitute in what we now know. So we said y, well, we're going to call that h for height. So your h is equal to our k, well, that's 5, times our a, well, that's 0.7, so we'll just put that in brackets, 0.7 to the power of x. Well, x we said was going to be the number of bounces, or n. So our equation is h is equal to 5 times 0.7 to the power of n. Now the next part of the question says find the height of the ball after 4 bounces. So what we're going to do is go through and write out what we know. So we now know our equation, which we can use to help us out with this. So that is h is equal to 5 times 0.7 to the power of n. And what we also know is that we've got 4 bounces, so n is equal to 4, and we're looking for the height, so h we're going to write as question mark. So let's go through and substitute that in now. We've got h is equal to 5 times 0.7 to the power of n, well, that's 4 now, and what we're going to get when we put this into our calculator is an answer of 1.20 meters. Now for part B of this, we've got find the height of the ball after 6 bounces. So we'll write out the equation again. So h is equal to 5 times 0.7 to the power of n. Once again, we know that our n is equal to 6 this time, and we're looking for our height, so that's going to be a question mark. So what we're going to do is go through and substitute that in. So you get h is equal to 5 times 0.7 to the power of 6, because that's our n value. and when we go through and substitute this in, we're going to get an h value being equal to 0.29 meters. Now finally it says sketch the graph of the height of the ball after n bounces. Well, we know that the initial height is going to be at 5 meters, so this is kind of like the height that it starts off at there. Alright, and we can write in our coordinates, as you can see, as being 0, 5, because it's an n coordinate of 0 and an h coordinate of 5. Now, we know that after 4 bounces it's going to be at 1.2 meters, so let's go over to 4 bounces, which is here, and up to 1.2, and we'll plot the dot, and we'll just write this in as well as being 4, 1.20. Now we also know that after 6 bounces, well, we're going to be at 0.29 meters. So we'll go across to 6 here, up to 0.29, which is just halfway, and we'll write bracket 6, 0.29. Now when we go through and sketch this, what's going to happen is we know that it's going to start off at 5, it's going to come down here like so, through both of these points, and as we can see it's going to get closer and 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 closer to the height of 0, but it's actually never going to touch because it's an exponential function. Now there's no point in actually drawing an arrow that goes up here because we can't have any negative number of bounces. We'll just leave it as starting off at 0.5, but we can actually have an arrow that goes along here. Now if we think about this for a little bit, of course the ball is going to come to a standstill eventually and it's not going to continue bouncing, but this graph actually says that it's never going to stop at a height of 0. So of course our rule is limited in the way it can represent what's actually going on, but you can see it's going to have a fair representation of what's actually occurring.
Alright guys, so I guess at the end of the day it really doesn't matter what the question is as long as you follow those 4 steps. That is, 1, you read the question carefully so that you understand what it's actually asking you to do. Now in step 2, go through and highlight all of the key information so that way you're starting to bring out the key mathematical content from within the question. In step 3, go through and rewrite this stuff that you've highlighted in clear, concise dot points so that way you really understand what mathematical content is hidden within the question. And this is actually going to help you out when dealing with step 4, where you might have to go through and write out a mathematical equation to represent what's actually occurring. Now, thank you very much for tuning into today's lesson, and of course, make sure you stay tuned for the very next lesson. Like always, make sure you say hi to your maths teacher for me. Aussie out.